Hi everyone. In this video we're going to be looking at Chapter 2, just doing a fairly quick overview of the chapter itself and just pointing out some of the big ideas in here and trying to make connections to what you've already seen. So this is going to be the chapter where we try to bring everything from Chapter 1 together, give some names to things, and then just keep practicing, keep trying to learn the ideas. So we start in Chapter 2, Section 2.1. And the main idea from this section is called hypothesis testing. So we've already thought about this. We haven't put a name on it yet, but this is the idea, the big idea, hypothesis testing. And so what we're going to do is each problem, we're going to be given a scenario, some information, and what we're going to do is we're going to be testing a specific hypothesis. So you can see that word kind of popping up a bunch here. All right. And the way that this is going to go is there are going to be two of them, your null hypothesis and your alternative. And here's the thing. Every problem is going to come down to this. Somebody in some way is making a claim about a parameter. So when you're looking for this in a problem, right now it's pi, it's mu. It's percent, it's mean. Okay? So that's the thought bubble you should be having when you are starting at a problem. There's a parameter in here. It's a mean or a proportion. So I'm looking for words that help me figure that out, right? And then I'm going to start this process by saying, okay, I figured out what the parameter is, what I'm measuring here, this idea. Now somebody's making a claim about it. We've already made some claims and done this already. You've already done some of this work. The example I have down here is us doing work on the fair coin. I give you a coin. I claim it's fair. You guys have done a great job saying, okay, I know what that means. I know that means that it should get heads 50% of the time. So see what you did there. You took a claim. So right here, you took a claim. This is my claim, fair coin, and you converted that into a value for the parameter. Remember, pi here is that long run proportion of heads, right? What happens when I flip the coin a bunch of times? Well, if I say it's fair, you can put a number on that. That's your null hypothesis. You get a problem, that's what you're doing. You're finding a claim somewhere about the parameter, and you're going to put a value on that claim, right? And so the setup of this, HO, will be put your parameter down, always pi or mu for now, always an equal sign, and then you put the number that you have here. For a fair coin, it's 0.5. If we're rolling a die and we want to know one side of the die, it's 1 out of 6. Put that there. Rock, paper, scissors. If people are just randomly throwing, what's the probability you get scissors? 1/3. You put that there. We had problems where we were looking at things like in the last homework, you had the National Health Survey said that the average height of men from age 20 to 29 in that age range was 5 foot, whatever it was. That's a claimed value. That would go in your null hypothesis. Then the next thing that we haven't really done, so this is a little bit newer, is you're going to set up something called the alternative hypothesis. So the alternative hypothesis is this one. It's the alternative to that. If you're telling me my coin is fair, 0.5, right? That's my fair coin, my null hypothesis. Then my alternative hypothesis is just what's the opposite of that? It's that the coin is not fair. Opposite. Okay, so it's the opposite in some way of your claim. And so not a fair coin is the opposite. And so what do? You take this and you somehow figure out how to use math to represent that. So if it's not a fair coin, then the probability of getting heads, the long run proportion of heads when I flip, should just be not 0.5. I don't know what it is. I'm not saying it's something specific. I'm just saying it's not 0.5. And what we'll end up seeing here is there's a little more to this, in that this symbol here will have some options. So the options we'll end up having are not equal to, greater than, or less than. And what we'll do is we'll decide that based on the problem itself. If I come up to you and say, I have a coin. I think this coin is flipping heads more often. Then you would set up, okay, well, fair coin, still my null hypothesis, because it's this null, nothing interesting. That's one way you can try to remember this. The null hypothesis, boo, nothing interesting. The alternative then, okay, would be, oh, okay, something is interesting is going on here. Something interesting is happening. It's flipping greater than 50%. So this can change a little bit, but you should still be thinking in some sense opposite of the null. All right, so null hypothesis, this original claimed value, this boring thing, the nothing interesting is happening. This next one, the alternative, opposite of that. Something interesting is happening. Fair coin, not fair coin. So we'll set those up. Step one, all these problems, boom, we're going to set this up. Then we're going to do something we're also used to. We're going to talk about the sample. We are doing inferential statistics. There's a big population. We want to learn about it, the parameter. We can't get to the whole population. We go to the sample, we get a statistic, and we try to use that to infer something about the population. Okay, so that's what we're doing here. Inferential. We're inferring something about the big group. So this part we've already done, right? We've already done this. We've looked at statistics, p-hats, x-bars. We've gotten sample sizes. We've done all this. What's new here, so, what's the new thing here is we're going to talk a little bit more about the idea of how do you get a good sample. So everything that we're going to do here, all of our work, relies on the fact that our sample is representative. So my shorthand for this is it looks like. You need your sample to look like your population. Okay? So the sample needs to be representative of the population. It's got to look like it. Okay? And so the best way to do this, what's our best way? Is to do a random sample. Okay? So this is how we want to do it. It's not always possible, but this is our best way to do it. And we'll talk a little bit about how can we try to detect samples that aren't representative from the way we gather them, and talk a little bit about that. So, but mostly this is new, or this is not new, sorry. Mostly this is stuff we've already seen. We know what these look like. Okay, step 3. We've already done this too. So, big key point here, create a distribution of sample statistics. We've already made these pictures using the applet. So I'm continuing my example from above here, where you told me fair coin. Okay, that's my null hypothesis, my nothing interesting. I take that number that you get me from fair coin, I bring it down here and I say, okay, computer, I want you to take samples, just like I did up here, from my actual sample, right? I want you to do the same thing, except assume the null hypothesis is true. So assume the null hypothesis is true. So we've already done that, right? We've already gone into the applet and say, computer, pi is 0.5, pi is 0.333, pi is this, mu is that. We've already done that. Now we're just saying, oh, we've done that because that was our null hypothesis. Nothing new here. You will just now have written down this number, this symbol, and then you'll go, okay, time for the applet in step 3. Just grab this number, put it in. All right. So we've already done step 3. We're just putting a name on some things, but this has already been done. We're just going to keep doing it the same way. What about step 4? Well, we actually already did step 4 too. Step 4 says, Identify if our observed statistic, what we really did, is usual or unusual. Okay? Comparing to this distribution, comparing to this assumption. So I assume a fair coin, then I do my flips, and I compare it to this picture. We've already done that a bunch of different ways. Just looking at it, some calculation, all of this we have done. So we started talking about the 2SD method, end of chapter 1. All of this still applies. All right, and so what we're going to do, what's new then, right? If all of this is old, what's new? What's new is we're going to finalize and put names on 2 methods to do this work. All right, so one of the methods comes directly from what you've already done here. Okay, we're just kind of going to repackage it a little bit, and we're going to make it actually a little bit quicker to do, but it comes straight from this. Okay, and that is actually section 2.3. So let me scroll on here. So section 2.3 is us repackaging the 2SD method. So this is where the 2SD method comes in. So it actually applies in both sections, but this is where you'll see the direct connection. And so what we'll do is we're going to define this new idea in quotes, right, because it's not really new, called the standardized statistic. So what we're going to do is we're going to take our statistic, and then we're going to do a calculation using our statistic, and basically all it's going to do is it's going to tell us how far our statistic is from the mean. That's what we're going to do, is one calculation. There's only 3 numbers in here. 3 numbers we've already worked with a bunch. So in the 2SD method, so it's all connected, all right here. We're going to do our statistic minus the mean of our distribution, okay? And then we'll divide by this number called the standard error, which we're going to have to talk a little bit about what's going on with that, why we do that. But just believe me now that this is something we'd want to do, this division. And in your head, you can just remember it as, okay, I just need to measure how far away my stat is from the middle. Further away, more unusual. Close, more usual. We've already done that a bunch. What have we already said? Oh, if I'm 2 standard deviations away, if I hit that cutoff or more, I'm unusual. Here's the thing here. I was going to say the tricky thing. It's not tricky. This calculation literally just says how many standard deviations are you from the mean. So instead of calculating 1, 2 standard deviations out and then bringing our statistic and trying to figure out where that goes, we don't do that. We instead go, I'm not going to do that. I'm just going to ask, how many standard deviations am I away? If I'm more than 2, unusual. If I'm inside that 2 range, usual. So we already did this. It's just a reformatting it so it takes a little bit less time. It's called the standardized statistic. But that's all this calculation does, is literally just say, how many standard deviation jumps did I have to go until I got to my statistic? If I had to go 1, 2, 3 jumps to get to here, unusual. If I only had to go 1 standard deviation jump, usual. That's it. That's all this calculation is. So we've done that. We're good on that. We'll practice it, of course. We'll talk about it, but you've already done this. The one that was just brought up right at the end of chapter 1 was this idea called the p-value. So this one's going to be a little bit newer than the standardized statistic. But it still uses all of the work we've done, okay? And so all this p-value is saying is, if it just so happens that your statistic is in this outer 5% to start of all of these samples, then you're unusual. That should sound really familiar. We talked about that, right? 95% inside's usual, 5% outside is unusual. So, okay, all right, that's hopefully not too bad. we call that percentage that you're in, that outer percentage that we calculate that you're in, we call that the p-value. Right? So what we're going to do is, again, this is like we're just flipping it. Instead of figuring out on this picture exactly where the cutoff is for 5%. So what did we do last chapter? We said something like this. Here is the cutoff, maybe, for this picture, where it was, 95% in the middle, 5% outside. So we did that calculation. We figured out where that was on the picture, and then we brought our stat in, right? All this p-value is doing is just going the opposite way. It's saying, wait, don't do that yet. Why don't you just take my stat and figure out, okay, you put the stat right on the picture, right? Throw the stat on the picture, and then just tell me what percentage, right here, what percentage of these samples are at that point or more. So we're asking kind of how extreme are you out there? And if that number is really small, then that means you're very extreme. You're in that outer regions, those outer percentages. If that number is big enough, right? So let's say my stat is a little bit less extreme, right? As my stat goes in, maybe this is my stat now, then a larger percentage of the samples are going to be at that point or more extreme. This would still be unusual, but then again, the stat, if my stat gets a little bit closer, now I'm over here maybe. Here's my stat. Now, the percentage of samples that are at that point or more extreme, now that's too big of a chunk, and I'm past our cutoff of 5%. And so at that point, we're going to say, okay, you're usual. So if you've gotten in your head the 95%, 5%, if I'm in the 5%, unusual. If I'm inside the 95%, usual. That's exactly the idea we're using here. We're just kind of turning it around. All right, we're thinking of it from the other direction. Previously, you calculated the cutoffs and you just said, okay, here are the cutoffs. Now put the stat in there and tell me where it is. We're just going the other way. We're not calculating the cutoffs. We're just doing a calculation for your stat itself. And just remembering 95% in the middle is usual, 5% on the outside is unusual. So it's going to take a little while to get us kind of ready to go for this, but that's okay. Just always go back 95%, 5%. And then the other thing we're going to talk about here is this thing called the significance level. And so this idea is just to start, alpha is a symbol. We're going to start with this as 5%. Okay? And so we've been using, last chapter, beginning of this chapter, our cutoff is 5%. If you're in the outer 5%, you're unusual. Inner 95, usual, right? And I just said, believe me, 5%. Well, we are actually going to talk a little bit now about, well, what if I don't want that as my cutoff? What if I want my cutoff to be 0.01, 1%? Why does it have to be 5%, right? What if I really want a more, like a really extreme thing to be unusual, triggering unusual, right? I need to make that harder to get to. Then you would change your alpha. And so we'll talk more about this. It's really not too bad to kind of dive through, but it basically just is us taking that picture that we have here and that 95.5 and saying, instead of driving those nails into the ground so that it's usual 95 inside, 5% unusual outside, we're just moving the goalpost a little bit for alpha. Okay, if I make alpha smaller, like I did in my example there, I move the goalposts out wider. I'm going to start calling more in the middle usual and less unusual outside. So we'll do examples. We'll play around with it. It's significance level, just moving the cutoff. That's it. And we'll talk a little bit about why you would do that in certain scenarios. A lot of the time, 5% works just kind of all over the place. 5% is all good. But there are scenarios where you might want to change this. You might want it to be a smaller number or a bigger number. All right, we'll talk a little bit about that too. Okay, so that's really all of chapter 2. I mean, it's definitely a good amount of stuff, right? But a lot of it is based on things you've already done. So in terms of new stuff, it's mostly just new names for things you've already done before. So we just got to keep working on those same ideas we've been using. We'll do some practice, and then we'll keep going. And then you'll just notice that we're just going to keep using this over and over and over again through the rest of the course. So this is the big chapter where we try to really bring everything together and try really hard to get a lot of these core ideas down pretty good. So read up, do your reading, do your practice, and I'll see you in class.